welcome to the Artificial Intelligence Precision Health Institute's Affinity Group. Here we listen to leaders in the field and discuss trends in AI and healthcare and bring together AI researchers in a variety of fields, and especially with clinicians and advocates to further understand the trends and incorporate them into what we do. Our overall goal is to foster these collaborations, solve problems in cancer and in medicine that were thought to be unsolvable decades ago before the broad use of deep learning. The format's roughly about 30 to 40 minutes for the talk, and we have an interactive session after that. So please stay for the discussion. It's usually the best part of the meeting. The IFI Infinity Group is brought to you by several entities here in Hawaii. First, the University of Hawaii Cancer Center and on the Kaka'ako campus. Also, the AI Precision Health Institute itself, which fosters graduate students to work in these topics. And also the Hawaii Data Science Institute, which is a coordinating effort for data science across the university and its fields. We would provide a very generous speaker compensation of a IFI sign, and we'll be sending yours in the mail. I hope it's okay if you can receive that as a government employee, Dr. Liu.
I doubt that, but thank you for the gesture. Yes.
Well, our paper of the month is that's called MedCalc-Bench, Evaluating Large Language Models for Medical Calculations. And on this paper, Dr. Liu is a senior author. If it is available from, it's available as a PDF without any fees associated with it, and I encourage everybody to take a look at it. I think he'll be speaking more about that today. So it's my pleasure to introduce Dr. Liu, a senior investigator with tenure at the NIH Intramural Research Program and deputy director for literature search at the National Center of Biotechnology Information. He's a leading expert in AI, biomedical text and image analysis, and information retrieval, playing a central role in enhancing tools like PubMed, LitCovid, which are used by millions of people around the world. I just want to note that this marks the 18th year, I believe, of Dr. Liu's service at the NIH, a tenure that reflects really an ongoing commitment to this field and accessing information. And so I appreciate that, especially in these unprecedented times. He's a fellow of both the American College of Medical Informatics and the International Academy of Health Sciences Informatics, and currently serves as the serves several key federal AI committees. He's authored over 350 papers. His H-index is 80 with more than 40,000 citations. So Dr. Liu, welcome to the IFI, and we look forward to your talk.
Thank you. Thank you very for the kind invitation and the introduction. So just checking, you can see my slide?
Yep.
You're good. All right. Well, thanks again. So as introduced, I come to you from the NIH Intramural Research Program. Specifically, my IC is National Library of Medicine, where I lead a research group using AI and machine learning for both biomedical text and image processing. So on a routine basis, we work with tens of millions of papers in PubMed, full-length articles in PubMed Central. When access is given, we also work on EHR patient data. In the last couple of years, we have also reached out and branched out and doing some patient images, in particular in ophthalmology and radiology, because we have wonderful clinical collaborators on the NIH campus. So even though I was invited for that particular MedCalc-Bench paper, but I thought I would give you a little bit broader agenda today, talking to you three items. One is our research related to biomedical search and information extraction very quickly, and then talking about two use cases of the generative AI and the large language model, one for patient matching, one for automating medical risk calculation. So I'll start with PubMed because this is something I think everybody is familiar with, and perhaps you're also a contributor to this database. You have your papers published and you have index in PubMed. What you don't know is perhaps on an average day, we have about 2.5 million users doing about 3 million page searches and 9.9 million page views. Now, this compares nothing to, the traffic in terms of traffic to Google search or other general search engines, but does make PubMed one of the top 3 or 5 most accessed federal government websites. As you know, from time to time, there's a government shutdown, but I can guarantee that PubMed lives 24/7 and still is up for business when that happens. Now, even though AI and machine learning is a hot topic today, but since day one, I've been at LLM, which John mentioned is about 18 years now, we've always thinking about ways that we can utilize computational approaches to improving our user search experience. Okay, so here is a list of search features that were extensively or exclusively implemented using computational AI and machine learning techniques. I don't have the time to go into the details, but one thing that differs ours from other search engine or commercial literature search system is that we try to be very transparent about what we do to our users. So for every search feature, some of them you may have familiar with, that you have used in real world, in real life, that we always publish a scientific publication or at least a blog post to explain how we used AI to implement these search features. In fact, a few years ago, we even write an article not only to reveal what's under the hood, but also how our users are responding to these features. Obviously, we worked on more than these features, but because we monitor user activities, we know what are the ones that users like to use versus the ones that they don't use that often. So these are the ones we actually, the ones that you see in the system, meaning that they are users' favorite tools. Now, obviously, my own favorite is the best match because this was the one implemented into PubMed a few years ago now that allows our users to look at the search results ranked by relevance rather than by reverse time order, which was the only option back in 5 or 6 years ago. But as a researcher, you all know that these days, if you have an information need, you want to find some papers, you can pretty much do that. It's not that hard to come up with a few keywords, like the 3 or 4 keywords to find papers to read. The problem is perhaps the opposite, that having a 3 or 4 keywords, you enter PubMed, you also enter Google Scholar or Google, you get too many papers returned. Sometimes that's hundreds of papers, sometimes that's thousands of papers or tens of thousands of papers. So for a single researcher, we just don't have the time to go through that long list of papers, not to mention opportunities to make the hidden connection between these papers. So the million-dollar question for a long time for us is there a way that we can teach computers to read or scan the papers just like the human scientists? So toward that goal, we have developed some using NLP, natural language processing techniques, to extract knowledge, to recognize what is the gene, what are the diseases, what are the drugs or chemicals described by the authors in the papers. So we have tools. So here I showed you 3 different tools. Some of the tools are very disease specific. For example, LitCovid was specifically created for the past pandemic. The LitVar perhaps is more interesting to you if you are talking about precision oncology, which really extract the phenotype-genotype relationship about, tell you everything about a particular mutation, what has been described in the literature. And then we have tools like PubTailor, which covers millions of concepts of all different concepts and their relationship, genes and disease and what that relationship. In my view, I call PubTailor basically a PubMed on steroid. Not only you have the content of the literature, but you also have these machine annotations, as I show you on the right side. And all of these are made publicly available. And as you can see, some of the tools has gone through multiple iterations. The reason we have, we separate Litvar, for example, from PubMed is because for Litvar, we've gone through not only just looking at the annotations in the abstract, but also in the full text. And not only in the full text, but also we've been repeatedly told by our users that you need to mine variants in supplementary materials. And that's the specialized version we actually touched supplementary materials. In other cases, to be honest, I'm reluctant to touch the supplementary materials. As you could imagine, people put all kinds of different data in supplementary materials and different formats. It could be PDFs, it could be tables, it could be Word files, it could be spreadsheets, and it could be images. So it's very hard because of that. It could be very hard. It could be very noisy to get the reliable information out from the supplementary material. So for PubMed, we only text mine abstract and full-length articles. So we just like what we did for PubMed, we know these tools. We make it very easy for people to utilize these different tools as long as they have access to internet and web browser. They can look at the results for individual articles, and if we like them, they can do more using programming APIs. Now, obviously, the reason I say if they like them, because I know for sure, I can tell you upfront that none of these text mining algorithms can recognize the gene names or disease names with 100% accuracy. Okay, but look, if we ask two biologists to annotate gene names for the same article, even the same abstract, I can guarantee you they're not going to likely agree with each other also. Okay, so not a perfect performance does not mean this is useless. It rather, if they look at this and they find this is good enough, they can utilize for a wider variety of downstream applications. And that's why over the years, we have had over 1 billion access when combining both the web-based visits as well as people retrieving annotation using the APIs. And I showed you here, we have actually pretty much visitors from all of the world, including people living or working in Antarctica. And I showed you also a bunch of different institutes, because oftentimes when I make a presentation at a conference, people would later come to us and say, we actually are a user of your systems. Other times they just send us an email starting with, thank you for your service, but can you help us with this or other request? And other times they just say, can you correct this? Your system seems broken today, which is not the end of the world, because if you provide a system, I actually like to hear from our users, good or bad. I think it's much better than you set up something and you never hear anything from your potential or targeted users. So this actually concludes very quickly, very briefly, the kind of tools literature mining tools that we have conducted over the last 15, 20 years at the NIH. And we're still doing that because I still think there's a lot of things we could do on that. But I think the main reason I was invited here because everybody is very interested about the applications of large language models. And I have to admit by myself as well that in my 20 years of doing research with AI in medicine, I've never seen something so powerful or so amazing in terms of capability for language generation and understanding. And that makes no wonder it took only 5 days for ChatGPT to grab 1 million users compared to much longer time, compared to some other very popular online services and applications. So you probably have heard of some of the early wins of ChatGPT. A boy saw 17 doctors over 3 years for his chronic pain without any diagnosis. But eventually his mom typed his symptom in ChatGPT, and ChatGPT was able to find the right diagnosis. Now, obviously, it made the news because this is cherry-picked, okay? But you also perhaps have seen that when ChatGPT was launched, it showed amazing performance on some benchmarking tasks, and one of them widely cited is its performance on the USMLE medical exam tests. these are the ones for testing medical students in this country, and the passing score is 60. And when it was first launched in November 2022, it was already have a score passing 60. And then within a short period of 6 months, it reached close to in the 80s and very close to the attending level performance. I'm pretty sure now it's over 90 or even close to perfect. And I have to say that we're now so used to this amazing performance, but for someone who worked on this field for a while, that I really appreciate the fact that it was able to achieve such amazing performance, because for a long time, just before, let's say in November 2022, for a long time, people worked on this. They have used all types of AI methods, including the methods, the previous generation of transformer architecture, and the performance was in the 30s and 40s. And if you at the time you can bring your performance accuracy over a 1 or 2%, that's considered very incredible, very amazing. So to me, at least, I didn't expect or didn't foresee this was coming in such a short period of time. But what has been evaluated in the USMLE is like example shown here. And this is the limitation of such benchmarking is this not really is a real world task. For one, and for the most important one is in real life, when the physician look at a patient vignette or patient notes, there's no ABCD to choose from. The multiple choice question is certainly not a real world task. And more importantly is that when we testing AI on these MCQ questions, even the answer is correct. Does it really mean that AI understand the question and using the right knowledge and the right reasoning to get the right answer, or it just happened to find the right answer? Because we all know that when we do this, when I remember when I was in a school as a student doing multiple choice questions, there's different strategies you can use to maximize your score. Not necessarily I understand every question correctly. So one of the studies we did was that because of that question we had in mind. So when GPT-4V, which is the multimodal GPT-4, launched in November 2023, now it's almost a year and a half now, we quickly jumped on this and to do a benchmarking evaluation study. And our two scientific questions were, number one, how does this multimodal GPT-4 model able to answer visual question answerings? So given a pair of text question and a medical image, can they quickly pick or doing the diagnosis correctly? And how does that compare to human performance, human expert performance? And number two, perhaps more interesting, is GPT-4V or is AI making its decision based on some rationales? And we investigate this rationale from 3 different aspects. One, or 3 different angles. One, does the AI understand what's in the image? And number 2, does it use the right knowledge to answer the question? And third, based on the knowledge and what's in the image, does it make a sound reasoning step to generate the final answer? So to do this, we collected questions just like shown in this slide, like 200 of them from the NEJM online image challenges. So every question has a patient text vignette as well as a medical image. And then we used the web version of the GPT-4 that was just launched at the time. And then we invited domain experts that includes 1 MD student and 9 physicians. So as you can see, these 200 questions cover a wide range of different specialties in medicine. We have cardiology, we have dermatology, we have ophthalmology, so on and so forth. And then we have different image modalities as well, including pathology images, including CT images, including MRI. And then what we did was we give these questions to AI, and we give these questions also to the physicians, okay, human human physicians. Now, we only ask the physicians, for example, to answer the question in their specialty. So we only given the 34 dermatology questions to dermatologists and only ask them to answer them and then compare it directly with the AI. Furthermore, another use of human physicians is that we further ask them to make assessment or evaluate the three aspects, the three rational aspects that AI generated. So let's look at some quick results. So the first results showing here, perhaps not that surprising to you, is that physicians really are have more training than the medical student. Okay, we would be very surprised otherwise. And students are getting about 60% accuracy, and physicians are getting about high 70s. And then in this case, I'm showing here is physicians are operating or answer those questions in a closed book form, which means that we did not allow them to consult a colleague or using Google search. Okay, and their performance is on par with the GPT-4. GPT-4 has 81, but given the small number of test questions, they're not statistically significantly different. When physicians were allowed in the second round, when they were allowed to do Google search or using any resources they have access to, their performance is actually in the 90s. Okay, so they're still performing better in that case. But perhaps the most interesting results is the second part to answer the second question. When AI gets the answer correct, does it really understand the image, or does it really using the right reasoning to given its final answer? And what we find is that over 1/3 of the time, when it's generating or when it's producing the right answer, 1/3 of the time, there's some flaws in its reasoning process. And mostly it's because they did not seem to read the image and understand the image correctly. And then other times followed by using the right medical knowledge or the reasoning part. So I want to show you quickly an example of the image comprehension aspect. Now, I'm not a physician. I'm trained as a computer scientist. But even for me, I can tell there's a difference between the two eyes on this MRI image. But GPT-4V's interpretation is there's no abnormalities in this particular image. So clearly, there's something not that correct, even though in the end, GPT chose the correct answer for that particular question. Okay, so I want to put up this first because all the study use cases I'm going to follow sort of to highlight their potential benefits of using AI. But just because of that, I think today's AI performance is so close to human performance, and because that, it's perhaps more important than ever before to look at its potential or hidden flaws or potential limits, because the AI today, these days, are so close to be used in real life. Okay, but having said that, I'm truly a believer of this technology, don't get me wrong, and that's why I'm going to show you two use cases quickly, that how we using AI, how we take advantage of today's large language models for important tasks in medicine. And the first one I want to mention is, I think this is a signature study of our lab, and we're still working on this. So this is a very ongoing active research, even though the first paper was published in November last year, where this also got a little bit of a publicity, not because us, I think really because clinical trial is fundamentally very important for evidence-based medicine. And at the same time, there's a real world needs both within NIH and outside to speed up this patient enrollment process, because it was estimated, I think somewhere I saw, over about 25% to 30% of the cancer trials terminated because of insufficient enrollment. So we started this project actually, and then in the middle of that, we were approached by physicians from NCI because they were basically telling us how challenging it is for them to actually matching patients referred from outside of NIH to the clinical trials being conducted at the NIH. If you've been at NIH, you know that we have on the main campus in Bethesda, Maryland, we have actually one hospital in Building 10 called the Clinical Center. And the main reason of the Clinical Center is to support clinical research and clinical trials. We don't generally see usual diseases at the clinical center. It's mostly for research only. So the system, we were told by our physicians, it takes days, sometimes weeks, even longer for a patient referred from outside to get a decision, initial decision, whether there's a match to some of the trials conducted at NCI. So our goal was to see if we can increase that, shorten that time and increase the productivity and make it more efficient. Now, obviously, using AI to speed up trial matching is not a new problem. People have made effort, a lot of attempts in the past, but I'll say that generally speaking, there are two major limitations. One is that previous AI basically works this as a black box. You're given a patient notes, a pair of patient notes and a clinical trial document, clinical trial as the input, then basically you're getting an answer yes or no without any explanation why. And this is not ideal because we're talking about not using AI to replace human decision making, but rather using this as an assistant. So if you're going to using AI as an assistant, then you got to tell the end user why we should trust your decision. And therefore, transparency is very important and it's actually a necessity in this kind of work. Number two is that previous embedding-based approaches to work well, you require a large number of training data. And so you can create, first of all, creating training data is very expensive. Second of all, this may not be generalizable to different diseases areas in medicine. So what we like to do is to do a zero-shot learning fashion using large language models. But what's nice about these previous approaches is that because of them, we are very fortunate that grateful that there has been already some benchmarking data set created in the public. There are 200 patients and 20,000 trials, and pair of them have been manually annotated to serve as the ground truth. So thanks to a very bright student and trainee postdoc in my group, Dr. Jin, he created what we call a TrialGPT using the large language models. And what's unique about this framework is that instead of just giving a and yes or no binary answer, his design would ask large language AI to look at each individual inclusion and exclusion criteria of a clinical trial, and then to evaluate not only whether this patient is eligible for this particular inclusion or exclusion criteria, but at the same time to provide two other additional information that includes explain to us what information in the relevant sentence in the patient notes that actually make AI to make that decision about eligibility. So this, first of all, has two major benefits. One is it already served as the explanation to the end users. So it's very transparent to the users about the AI decision. And number two is that actually asking AI to provide these explanation helps to minimize the known issue of hallucination. Okay, we're not able to say completely eliminate hallucination, but asking why this actually helps to mitigate and reduce the chance of a hallucination. So I show you here example, exact example how we did this. So on the left side is the patient notes, and on the right side are two inclusion criterion of a particular trial. So TrialGPT would look at the notes and then say, for example, the first inclusion criteria is traumatic injury to the head has occurred. AI says it's a yes, but also at the same time, it says that from sentence 2 and 3, there are relevant information because the patient hit her head on the corner of the cabinet and developed a headache. the next morning. Okay, so those are the detailed explanation that we asked AI to produce, along with the decision related about the eligibility for each inclusion and exclusion criteria. Now, how do we know this works? Well, so the only way we would know that is that we have human evaluation. So we recruited 3 MDs, which I showed you earlier. They helped us to evaluate 1,000 such patient criteria pairs. And based on their human evaluation, they showed that we're very high accuracy achieved in the high 80s. Okay. And what's even more encouraging is that we also asked them to do that without AI themselves. And we found their performance is also, like I said, they're not perfect either. They're in the high bulk of very close with the TrialGPT performance as well. Now, even though TrialGPT AI is able to achieve 88, 87 accuracy, there are still 12% of errors, or 12% of time that they make some errors. So we did the detailed error analysis. We find there are 2 main categories, error categories. Number one is, as you would imagine or know, that there are all kinds of things people put in electronic medical records, a lot of abbreviations, a lot of misspellings, so on and so forth. So for one, that for a lot of the TrialGPT or AI is basically unable to make the right decision because it does not know some of the medical knowledge. So in this example, for example, DSA, TrialGPT or AI just does not know what DSA is. Okay, so it basically gives the wrong answer. And then in another case is that its reasoning is still not as good as human. For example, there is a exclusion criteria for a trial, say patients with multiple AVMs, but in the notes it only mentioned 1 AVM. Now, as a human read this, I can probably interpret that because only mention 1, it means there are no multiple. But AI, because it does not explicitly mention there's no multiple, it just didn't get this question correct. But once we have these criteria level answers or judgment, then we combine them together on the trial level, and we compute 2 different scores. One is relevant score, one is eligibility score. Obviously, if you have a cancer patient, then the cancer trial will be more relevant compared to a diabetes trial, for example. But just because this is a cancer trial for a cancer patient doesn't mean it's the patient will be eligible. No. So we also have these 2 scores, eligibility score. Using those 2 scores, we can quickly rank the ones for a given patient. What are the trials that are relevant? What are trials that you can easily exclude? Because remember, there are many inclusion exclusion trial, inclusion and exclusion criteria. And oftentimes what we find is that it's very clear if the patient meets one of those exclusion criteria, we can exclude them. But oftentimes you'll find there's, for certain exclusion or inclusion criteria, there's just not enough information from the patient notes. So these scores reflects the relevance, and then we combine them to make the ranking. So we compared this because I mentioned there's previous work we compared on the evaluate our method on 3 data sets. And as you can see, the previous best method is able to achieve accuracy about 0.5, and these are based supervised machine learning algorithms using the supervised learning, while we're getting about significantly improved in the 70s in a zero fashion format. Okay, so this is quite incredible, I'll say, because of the capability of these generative AI tools. And because of this very promising results, we went out and did a pilot user study where we have 6 patient cases, real world cases, and 6 trials at NCI. And then basically there are 36 different combinations. Then we recruited 2 residents, and then we give them the 36 with and without AI and ask them to make the final decisions. And we find they basically give the same accuracy, but using AI, they were able to significantly save 40% of the time doing this matching process. So as I mentioned, with this results, we are so encouraged. So we went actually proposed to do this further sort of TrialGPT 2.0 project, and luckily last year we got awarded for the NIH Directors Challenge Award, and now we are working basically with expanding also because our work is in a zero short fashion, so we can actually looking at ways that we can expand beyond cancer. In particular case, Dr. Flanders, the collaborator on the co-author our paper, he's a neck and a head cancer specialist. But there are other cancers, for example, at NCI that we can look at. But there are also other disease areas that we can evaluate our AI. So this is something that we are actively working on, and I would be very since the paper was published, we have gotten approached by interested entities both from academic centers, cancer centers, as well as patient interest groups, as well as farmers, commercial entities. I'm not sure what we can do with the private sector, but we are certainly very happy as part of government to working with external collaborators to make this really a beneficial thing for patients. Now, quickly, in the last about 10-15 minutes, I'll talk about things that you caught your attention at the NeurIPS last year, which is our work of using AI as an agent for medical risk calculation. Now, for those of you who are not familiar, we're talking about clinical calculators. These are the tools used by physicians from time to time, according to a website which contains hundreds or even thousands online medical calculators. About 70% of US physicians using calculators every week. And this is just about the people using this particular website, but there could be more in real life. And on the right side, I show you one well-known or common clinical calculator for assessing community-acquired pneumonia severity. And as you can see in this calculator, called CURB65, there are 5 different parameters or variables, and then based on the patient information, the users will select one of the 2 choices here. And then in this particular example, it was there are 3 yeses and 2 nos, so it gets 3 points. And because of this 3 points, then the calculator, based on the primary research, they will say that this particular patient would fit into the severe risk group. There's a 14% risk of death in the next 30 days. So this is basically a tool that's being used in healthcare. But in reality, using such clinical calculator is not so straightforward, because as far as we know, these tools, clinical calculators, are not seamlessly integrated into the healthcare workflow. That means that first of all, physicians have to have knowledge about these tools and then know which tool is useful or relevant to their patients, and what are the most up-to-date information about these different clinical calculators. And oftentimes, because it's not well integrated, the challenge of using them also rises when physicians have to spend time to look at the patient information from the notes and gather the values for the different parameters. And sometimes the parameters are not even available to them, and then making the calculation. Given the little time we all know when doing a hospital visit or a patient visit, this is largely, I'll say, underutilized in today's healthcare. So because of these challenges we to address, we set up actually 2 very ambitious goals actually at the time, almost a year ago, again led by Dr. Jin and also postback Nick Wan in my group. So what we like to do is actually an end-to-end system to fully utilize large language models to first create these calculators, because all the calculators are published in the literature. Okay, now some physician may have knowledge about some calculators, but I can assure you they don't have knowledge for the entire spectrum of different calculators. And not to mention that these calculators do not exist in the computable form, so they cannot be utilized automatically or scalably or at a scale for processing EHRs. So the first thing we're asking AI to do, or AI as an agent, is to generate these calculators in Python code. Okay, basically by reading the literature. And once we have creating, we call it this tool curation part, and then given a patient, we would ask the AI to select which calculator, given this patient, which were the ones that are relevant, and then if relevant, can you make the correct calculation? Because you have to select the relevance, and then you have to look at the patient notes to find the values for these parameters of the calculator, and then make the correct calculation. So this is a pretty, I say, end-to-end system, and pretty also a big project. So we have, along the way, we have 3 different manuscripts. The one that you saw was published. The first was first published in December last year, and then we have 2 more that are under review that I hope that the AgentMD paper will soon be published by a journal. We are still making revisions based on the very thoughtful feedback from the reviewers. So in terms of tool curation, basically we call this AgentMD, this AI agent, to read the primary research papers and then automatically selecting, understanding the literature and curating those clinical calculators. Okay, so by reading the entire set of PubMed articles and doing the screening of the literature that are really talking about or publishing about these calculators, we are able to eventually curate over 2,000 clinical calculators. So what exactly we have for each of these 2,000 calculators? So here I showed you example. On the right side is the Python code. This is the computing logic of a clinical calculator live in a digital format, okay, rather than in a paper anymore. By reading the literature. On the left side is basically some of the text information, because not only we want to calculate the risk scores, but also we want the AI to interpret the risk scores to the end users. So for example, in this, the calculator that we used, showcased before, there are 6 levels of severity. So the one that we showed you in the example was a score of 3. So when score is 3, that means 17% risk of mortality in the next 30 days. So we did this as the first part component of the AgentMD, and we then, over the 2,000, we selected 100 for evaluation. 50 of them were most cited calculators in the literature, including the one I showed you in example, and another 50 we just randomly picked, because human evaluation of these calculators are very expensive, so we were not able to afford to manually evaluate 2,000, but rather just a selective 100. So what we found is that, again, they're not perfect, but we have about high 80s accuracy for both the computation logics and results interpretation. Some of the errors we have found along the way is that for mostly PubMed abstract is good enough as the basis, as the source, information source for generating these calculators. But in certain cases, they don't have enough information for these calculators. And well, you can say, why didn't you go to the full text? But I can tell you, not all the papers in PubMed we have the access to full-length articles. That's the limitation here. So we just go to the abstract. And again, most of the time, abstract contains enough information for these purposes. Other times, the AI fails to generate the Python code for some calculators, and other times they just incorrectly assign some interpretations. For example, even though they get the 6 levels of severity level correctly, but the percentage of risks may be wrong. Now, once we have these calculators, 2,000 of them, they're really in different buckets or different disease areas, then we want to use them automatically. And before we use them, again, we have to do some evaluation. So what we did is we created a toy data set. I call it a toy because the patient information is very simple in this case, and it's an open USMLE, again, multiple choices question format, test. But on this, but the point of this small toy test set is that we show you here in the two figure below is that basically the question is, this patient, the patient description, very short patient description, and below what are the risks for this particular calculator. You can see that using random pick, it's just 20%. Using GPT, default standard GPT with a chain of thought prompt engineering, it gets about 30% for 3.5, but then a big jump when we utilizing AgentMD. And same thing, if the underlying model is GPT-4, we have a higher performance. Now, at the time, GPT 3.5 and GPT-4 was the best model we evaluated. Obviously, today, we can do 4.0, 0.1, or DeepSeek. I would expect higher performance. But again, when we utilizing AgentMD, we would always, I hope that we will see that significant margin increase in performance, regardless which underlying model we use. Now, because this is, I call it a toy example, then we created a MedCalc-Bench paper where we actually have 1,000 of such questions, and with a more real world patient notes, which we collected from the articles published in PubMed. And then we have, instead of multiple choice questions, we have the open form answers for AI to score. And in that case, the performance is actually lowered significantly compared to what I showed you earlier. But I'm not going into the details on this. But I want to show you a couple of other evaluations we've done with AgentMD on the real data. Because all the ones that I showed you on the risk QA or the MedCalc-Bench were based on patient information in the published literature. And then we got connected with emergency department at Yale Medical School Medicine, and where we, through collaborators, they provided us 16 calculators their ED physicians very familiar with. Okay, and these are perhaps the calculators they use quite a bit. And then they also provide us about 700 patients, real patient notes. And then what we did was that for each calculator, we select the 5 most relevant patients that we for each calculator, and then we compute the risk scores for these 5 patients, and then basically 80 results we give back to the Yale physicians, ask them for them to evaluate, because we couldn't do more with the human evaluation. That's sort of the limitation we have here. But on the 80 cases that human physician reviewed, they find that 80% of the time for each of these calculator patients that we give them 80% of the time the patient are perfectly eligible, and then partial is another 10%. The only error is perhaps just 10%. And if the patient is eligible for that particular calculator, does mean that the second step is the risk calculation, automatically risk calculation correct. Well, half of them are perfectly correct. Another half of them are largely correct with some minor issues, which we call partial, which I'll have example to you in the next slide. And then final question is this calculation results really useful for you as a physician in real time decision making? And we were very pleased that 70% of the time they say yes, and another 20% plus they say partially yes, but with some minor cautions. But on the right side, basically show you that for each calculator, they are different. Some of the calculator, everything is 1, everything is perfect. Well, for others, their performance is much lower, and that's because different calculators have different level of complexity in calculation. Some of the calculators have many different variables that are very hard to extract from the patient notes. So here I showed you one example which we consider as a partial, because as you would imagine, some of the value for some of the calculation or calculator variables are missing in the notes. So when that happens, we ask AI to generate the best case scenario, to make a guess what would be or to make a guess about the range of the best case scenario or the worst case scenario. In this particular example, the patient respiratory rate is actually in the notes, 16. So, but the AI still makes the worst case scenario computation, which is not necessary. Okay. So in that case, the physician scored that as a partial correct. Without that worst case scenario, the answer would be perfect. Lastly, not only the calculator that we generated using AI can be used for decision making for each individuals, we believe this can also be a tool for generating population level insights, because these are really the tools that are made available in computer form. We can easily apply them to, for example, hospital, and given the hospital leadership or management some insights about the portfolio about their patients. So one example we did was to given them apply to the MIMIC3 data set, which is the ICU patient notes. So not surprisingly, we see at the very bottom of the slide here, we see that mortality is the #1 risk, okay, because we know that because this is an ICU patients, but also followed by cardiac risks in cardiac, in stroke, in respiratory, compared to some other risks like cancer, not for this particular patient population. At the same time, we find some of the calculators in our toolbox is way better than the standard GPT-4 if we're asking for mortality risk prediction. So to quickly summarize, I showed you basically some examples how we are doing these days with large language models, because as an academic level at the government, we don't believe we are in a position to competing with the private sector for producing the best and most accurate models, but rather we would like to evaluate these standard models on important healthcare problems. And along the way, because of our CS background, we aim to using our domain knowledge to improve these standard large language models. So whenever there are newer models, which doesn't happen every 3 or 6 months, we can always piggyback on these existing models and then further improve its performance. Like I said, I showed you examples of 2 important use cases. One is patient trial matching, one is medical risk calculations. There are certainly others that we can work on, but just as we appreciate the benefits of these AI techniques, like I say, we have another arm, which is to assess the safety and the limitations and the challenges of these AI tools, given that how amazing they are or how close they are to be used in real life. So even though I'm the presenter, I really present on behalf of an amazing team at the NIH, as well as our wonderful collaborators, both within and outside of the NIH. So I'll close here and thank you for your attention. Happy to answer some questions.
That's great. Thank you, Dr. Liu, very much. I'd like to go ahead and open up the floor for questions on this very interesting talk.